Good morning, everybody. Welcome to this early lecture. And thank you very much for the introduction and for the invitation to give this talk to this conference today. So as Thierry just said, I come from Zurich, where I have the chair of so-called risk safety and uncertainty quantification at ETH. So it belongs to an engineering department, and we basically develop all kinds of methods, algorithms for quantifying uncertainty in the context of engineering applications. So this ranges from what we call structural reliability analysis, of course model calibration, sensitivity analysis, and also optimization of systems under uncertainty. So these are a number of topics that we currently cover in the chair. This is main building of ETH. And today I will, as the title said, I will of course focus on sensitivity analysis, but from the point of view of using so-called surrogate models to compute typically sensitivity indices. So the starting point of my talk is the following. We use more and more models, computational models in all fields of applied science, engineering, natural sciences, and so on, to basically simulate the behavior of complex systems. And what I call a model here, a computational model, that's really, in the end, sort of a black box in which we have, at the beginning, a description of the equations, the governing equations of the system of interest. So it can be physical system, mechanics, and so on, but it can be also, I don't know, economists, dynamical model, or whatsoever. And then, of course, we need solvers for these equations. In most problems, we don't have analytical solutions. So this I also embed in what I call the model. This is basically the discretization technique, and then the solvers to, in the end, get results for the particular problem of interest. So these models, then, why do we do this? People used to, in the old times, to basically have experimental, physical experiments to better understand physical behaviors and test maybe prototypes and so on. So nowadays we use computational models to do this as far as we can. First of all, we have to make sure that those models somehow reflect the real world. So we have to calibrate them with respect to data, and the Bayesian techniques are very useful for this. We had a few talks on this yesterday. And once this is calibrated, then the point with these models is that then we can vary parameters and see what happens if we basically change environmental conditions, some design properties, and so on. So it's what people call exploring the design space. If we put on top of this an optimization loop, if we have some constraint, like I want to minimize the cost or the weight of a system, but while performing or fulfilling certain performances, we can put these models into an optimization loop and then find the best design. And finally, we can try to assess what's going on when we don't perfectly know the environment of our system and when we want to account for uncertainties. The point of uncertainty modeling is, I guess, very clear to everybody here, is the fact that there is always some differences between what we can design and compute with computers and the real world structures or infrastructures or systems that we are, in fact, building. So, for instance, if you are in, let's say, automotive industry, you produce a big number of cars every year. They are supposedly all the same, but you have always tolerances in the manufacturing in different geometry, thicknesses of different parts, and so on. So no two cars are really identical. It's the same for material properties. There is always some variability in the material properties used for constructing these systems. This is very much the case, for instance, in civil engineering. When you build concrete structures, even if it's a particular class of concrete that is supposed to be normalized and used, this will be built from the local material, and then you can observe scatter in the properties, and somehow this has to be taken into account. Now, if we consider, let's say, large systems and infrastructures, of course, a big unknown is the exposure, generally speaking, the loads that come from the environment. So it can be climatic loads, it can be natural hazard, earthquakes, floods, and so on. These things, we basically have some statistical models or some evidence from the past, but we cannot have, let's say, clear deterministic value what will be the largest earthquake in that area on the next 50 years to design, I don't know, a bridge or a building. So for all these reasons, we need some kind of uncertainty modeling and basically a probabilistic modeling of this. To organize all these ideas about uncertainty quantification, there is now, let's say, kind of a framework, a way of thinking those problems, which is quite well established. Probably you have seen different flavors of this scheme very often already. We really start by the idea of fixing what is our computational model and what is the goal. Why are we doing this or computing this? What are the inputs and the kind of output we are taking into account? So typically the kind of performance indicators that we want to fulfill, for instance, using those kind of models. Here, this is a finite element model of a structure. Then the next step is to identify the sources of uncertainty on the parameters. So really based on observations, based on expert knowledge, put together a model that reflects the state of knowledge you have on the system. So sometimes it's really, well, you observe scattering in parameters, so you have to model by distributions this scattering. Sometimes it's more that, well, there is a good value of that parameter for the particular system. It's just you don't know, so you put maybe some range to model and represent the lack of knowledge. So these are respectively aleatory and epistemic uncertainty modeling, and the two can be or should be taken into account. Then the next step is to, well, propagate this uncertainty through the model. That is, now the quantity of interest, consider a performance indicator maybe of a system. Now if the input is random, then the output is also random, and we are interested in statistics of that output. It can be a distribution itself, can be just maybe an average value or variance if we are interested in the variability. It can be something related to the tail of the distributions. That's where we are in the context of risk and reliability analysis. We basically want to typically compute the probability that the performance is not fulfilled or is beyond some admissible threshold. And of course, there is sensitivity analysis. That's the topic today. The more complex the system is, the larger the number of input parameters usually. And if you have many input parameters, then you are interested in the question, okay, but what drives really the output, the performance of my system? And that's the point of sensitivity analysis, really to get indicators of important versus unimportant variables, but also to quantify the contribution of those variables. Okay, so how to solve anything based on this problem, especially for uncertainty or for sensitivity analysis? I guess everybody's familiar with Monte Carlo simulation, which is basically based on sampling the input variables according to their distributions and then, well, propagating through the models or computing some sensitivity indices based on this. The problem with Monte Carlo, it's well posed, nice properties of convergence and everything, but very inefficient because you really usually need thousands to tens of thousands of runs to compute whatever statistics here with the sufficient accuracy. And for sensitivity indices, it can go to millions. We have seen examples yesterday. So this is obviously not compatible with complex models, complex simulators in which typically one run takes maybe minutes to hours. That's where we enter the world of surrogate models. So that's let's say the topic of today. So what is a surrogate model? If I call M, should have been written somewhere before, M is really this mapping between input and output parameters. So it's really your computer code. A surrogate model, M-tile, is an approximation in some sense of that model, which will be built on a limited set of runs of the true original model, which we sometimes call the simulator. So selecting some points in the input space and running really this complex computer code. And based on this, we want to build now something which will approximate this model on the full space, okay? So this we call experimental design here. And then, of course, we need, some more assumptions to do something meaningful. So then we choose a certain class of surrogate models, certain class of functions, which will allow to approximate the behavior of the original simulator. Here I give a number of examples that I will present in more details afterwards. For instance, polynomial chaos expansions, this surrogate model is nothing but a kind of orthogonal, kind of polynomial series. So here this will be polynomials in terms of the input parameters, and these are coefficients, well, that are to be computed for the purpose or for the problem of interest. So the unknown somehow here are just the coefficients of those polynomials. Later on, I'll talk about this quite recent technique called low-rank tensor approximation. So you can see here already it's a different setup, but again, there will be a number of unknown coefficients hidden in there. And the point of fitting that surrogate model will be to compute the coefficients. You may be more familiar with kriging. This will also be mentioned in the end. Here, basically, we assume that we can approximate the true behavior by a realization of a Gaussian process with certain properties, with a trend here, with some coefficients to compute, some variance, and some correlation structures to be defined. And there are many other ways, subprovector machines, neural networks, and so on. The point is that all these techniques, they are, or the way of using them, it's very similar. You start from what I have called already the experimental design. So you try to cover the input space of your parameters with points in a way that is really space filling. So really to cover all parts of this space, which leads to kind of visually uniform sampling if you have uniform variables in your problem, uniform distributions. But if you have other types of distribution, of course, this should be done according to the distributions. So typically, Latin hypercube maximin, Latin hypercube sampling, low discrepancy sequences such as Sobol points are the typical basic experimental designs that we use. Then once this is available, we have to run our model. Of course, we have to sort of generate some data from the true simulator. This is exactly as in Monte Carlo simulation. So basically, you take each input points, you run your model, may take a while, and then you get back the result. And then to really fit your surrogate model, you take advantage on really the two, the input and the output, as opposed to Monte Carlo simulation, where typically you would take a Monte Carlo sampling and just take the output points and compute statistics out of this, a distribution, a mean, a variance, whatever. Here, we really take the two, the input and the output, and we learn the unknown coefficients that you have seen in the previous table, okay? So depending on the type of surrogate models, you have different types of learning method. I call this learning method because there are many things that are similar or close to machine learning techniques. So for instance, for polynomial chaos expansions, you can use techniques based on projection and integration, sparse grid integration. You can use least square analysis, compressive sensing algorithms. In low-rank approximations, we will use alternate least square. If you know kriging, well, we use typically maximum likelihood estimation or cross-validation estimation, and so on. So these are techniques that are, let's say, specific to each kind of surrogate models, but then the main philosophy is the same. In the end, what we get? Well, we get something like this. That is, we replace a computationally demanding code where a single run may take hours by an approximation, which, of course, we have to make sure it's sufficiently accurate over the full space, but most of these techniques have built-in estimators, error estimators to do this. And that M tile here is typically something where I can use, I can compute 1 million of times the output on my laptop in a few seconds. If it's a polynomial, you can really easily, if it's properly implemented, you can easily compute the output or evaluate 1 million times the polynomial in a second. So the advantages, well, with respect to, let's say, classical just Monte Carlo techniques, it's very similar in the sense that all this is completely non-intrusive in the sense that we just need to run the model as it is. We don't have to change the model, get into the equations, or modify something to take into account uncertainties. We just take the model and run it for a number of pre-selected points. All these runs are independent, so if you have access to whatever high-performance computing infrastructure, this program is called embarrassingly parallel. So just run all these points separately in parallel and then get the results. And this can be very efficient. Where are the challenges? Well, the challenges is that we introduce an approximation. So we have to make sure that this approximation is correct. So we have to validate properly the results. And especially when you talk to people in practice to apply these techniques, of course, there is a bit more mathematics than doing Monte Carlo simulation. So this needs some effort in terms of communication. Anyway, in the end, in most of the applications or type of analysis I have mentioned already, there is a factor of, let's say, hundreds to thousands in terms, so 2 to 3 orders of magnitude, less computational time, meaning less number of runs of the complex model, to get the same accuracy on the quantities of interest, including Sobol indices, as you will see in a minute. Okay, so this introduction was maybe a bit long. Now let's go to the real core of this presentation. I'll talk about polynomial Gauss expansions first, then low-rank tensor approximation, and how we can get from those two surrogate models basically Sobol indices for free. That's the point. And then I'll just conclude or show some results for kriging as well. Okay, so what is polynomial Gauss expansion? Who has never heard about this in this audience? Bertrand, I know, yeah? Yeah, well, I mean, apart from a few people, you have at least heard about the name. So let me try to avoid, not to put too much mathematics on this and explain what's behind. It's actually quite straightforward. So the idea is the following, or the framework is the following. You have model your input parameters by a random vector. Here for a minute, or for this presentation, we assume that the components, the different parameters of your problem are independent. If it's not the case, we can handle this separately beforehand, but here for the presentation, let's assume it. So if now the output of your model, so the quantity of interest, think in terms of distribution of whatever you compute, as a finite variance, this is basically the only assumption, then we can write this equality, and here it's an equality. We can expand this output random variable in terms of an infinite series expansion, which is polynomial in terms of the input variables. So these psi alpha here will be basis functions, more or less, and y alpha are coefficients. So again, to visualize this, Monte Carlo, I guess everybody visualize. I have input space, I sample point, and for each point I get the output, and then I have many values, and I try to do some statistics. Here, it's really the structure of the output random variable that we want to approximate, and basically we define a basis in a particular abstract space, and then we will compute the coefficient in that basis. So that's why it's instead of computing things point by point, we introduce a structure somehow, and that's why it's very efficient. Now, what are these psi alpha? Let me tell you what it is. Here we need this concept of orthogonal polynomials. So what mean orthogonal polynomials is not just one written this way and this way, not this. It's based on basically defining an inner product of functions. So for each PDF of the input variables, we can define such an integral, here taking two functions, that would be an inner product. These functions will be orthogonal if this integral is 0, and this defines properly suitable Hilbert space and so on. And then the key point is that we can build families of polynomials of increasing degree that are orthogonal with respect to this definition of orthogonality. Okay, so if I have, for instance, a uniform distribution here, then the polynomials of each degree, the family of polynomials that would satisfy this kind of equation, meaning that the product of any polynomials different degrees 0 and otherwise non-zero, is the so-called Legendre family. And for Gaussian distribution here, this is Hermite polynomials and so on. So that's how to build so-called orthogonal polynomials in one dimension. Now here you see we have basis functions that depends on all input parameters. So how to make this basis, full basis, it's what we call a tensor product construction, but it's more or less a basic product. We will define a multivariate polynomial as a product of univariate polynomial in each of the parameters of the problem. Here, all along M, capital M is the number of parameters of my problem. Okay? Based on the orthogonality in 1D, actually, we get in the end an orthonormal basis also at this level here. And psi alpha here, each polynomial is defined by a set of integers which would be the degree of the polynomial in each variable. And then we have the total degree, which is more or less the sum of these integers. Okay, so this defines the basis, and well, assuming that you have a textbook on orthogonal polynomials, everything is there, so there's not much more than that. Let me visualize this here. This would be a problem with two variables. One, the first one is uniform over minus 1, 1. The second one is a Gaussian variable. So I can have in each dimension here linear, second order, and so on polynomials, and the resulting basis function, the resulting psi, is just the product of the two, function of x1 times function of x2, and then you see that we get more and more complex polynomials that of higher degree that would capture the local details of the true model. Okay, that's the basis. Now, how to compute the coefficients. So again, we could spend hours and hours to present all the methods available to do this. I just want to focus on one which is very straightforward in my opinion, which is more or less least square analysis. So the idea is the following. You have an infinite series, which is an exact result, and we can compute only a finite number of terms. So you have to select which terms. This we can discuss afterwards. But basically, you have a truncated series, and of course, all the terms that remain are the terms missing. So it's slightly different as the regular regression setup, because here it's not like a Gaussian error or whatever. It's modeling or taking into account every terms that are not retained in the expansion. But then in the end, to compute the coefficients here, we also want to minimize this error term due to truncation. So this leads to finding the coefficients here by minimizing the mean square error between the true output and this truncated series output. Question how to evaluate this. One simple way is just to sample the input space and replace this expected value of the mean square just by the standard average mean square error over a number of samples. Okay? So here what we need to do this is basically just to, well, first select how many coefficients you want to compute here. What people typically do, and this is okay, especially if you have not many parameters, is to take all polynomials up a total degree of whatever, 5, 10, something. So this gives a particular truncation scheme. Once you have this, you select an experimental design, as I have mentioned already, and then you have the results of the true simulator, the true model that will enter here. You evaluate also the polynomials onto the same points here. That defines what we call the experimental matrix. So all polynomials in this expansion at all points of the experimental design. And the mean square problem, well, that's a textbook equation. This reduces to a linear system to solve. Okay? So you get here this way the coefficients of the expansions. That's the minimal setup. And it's pretty simple to understand. Then there are different issues here, how to truncate. I mean, typically here, what is the degree to truncate? So we need for this a kind of error estimation. How can I be sure that I truncated at a meaningful degree such that my approximation is good enough? This we can handle in the following sense. What we want to estimate in the end, we replace m by a truncated series expansion, again written here. So the error is really this mean square error here, this estimation. Of course, we don't have access to this. If we were able to, or if we want to estimate this very properly, let's say again by some kind of simulation methods, we would need a huge number of runs of the true model to compare. So think this in terms of a huge validation set. And that's what we want to avoid in practice. Otherwise, if we are able to run millions times this, we don't need a surrogate models, of course. So this, we don't have exactly access. We have access to this here, which is called empirical error. So this would be the error, but just computed on the points that are used to build the model, the thing that we minimize here. And that is very bad in terms of error estimation, because this can be very well close to 0 or even 0, whereas the error is not at all 0. So this is called, this phenomenon is called overfitting if you find polynomials that really exactly fit the model at the points you are looking at, but is very bad outside. So to be somewhere in between, we have these so-called cross-validation techniques, which are used in also many other contexts. Let me show you leave one out cross-validation. It's a very intuitive way. Suppose that I have an experimental design pre-computed to fit my PC expansion. The problem of overfitting is to use the same points for fitting the polynomial expansion and then computing the error. So to avoid this, what we do is that we take one point apart, okay? That will be that single validation point somehow, and then we build a PC expansion with the remaining points. And then we compute the error with that particular PC expansion where the red point was not used. We compute the true value at that red point versus the PC expansion value of that red point, and that will be a local error. And then we do this on all points. Okay, that's the principle of cross-validation. This is a good estimator of the real generalization error. Written this way, you can think, okay, but then it's really kind of demanding to compute because you should not just have one PC expansion, but many of them, because you change the point that is used for validation. And in fact, it's not necessary because we can somehow recast or elaborate on this expression here to get the exact same value here, but that is estimated only after computing one single expansion that takes into account all points. So you see this error estimator is very close to that one, the same mean square error, except that here we have this kind of correction terms here that makes the thing much more robust compared to the usual root mean square error that people sometimes use. So with this, this is very nice because now whatever data you have, you can select a truncation scheme here, compute the coefficients, it's least square analysis, and out of this you get an error estimator. So this allows to now compute different or have different assumptions, for instance, on the degree on the truncation, and then, well, then take the best model you can get from your data. Just one word on what we call curse of dimensionality. The problem with the, let's say, basic approach described so far is that if you compute how many terms you have in such an expansion, taking all polynomials in the m input variables up to a certain degree p, it's this big number here, which explodes with the dimension. And the number of points you need to evaluate those coefficients is typically larger than that if you want to have this least square problem well posed. Typically at least twice this number to avoid like overfitting problems. So this can, well, be very large very soon. The thing is that when you do this, in fact, if you do this properly, in most common problem, most of the coefficients, in fact, are 0. Here I just show you without any details on the model behind, just one result. This would be a typical structural problem that we are confronted to, where we have this structure here. Think about these big beams you see in airports halls, for instance, and you have some loads on top, and you want to compute the deflection. You don't want it to be too large. This is a problem in which we would have 10 parameters here. So we can afford a sufficiently large enough number of runs of these models to get a good representation by PC expansion. And this would be now the coefficients of this PC expansion, which contains 3,000 terms. As you can see here, and the colors here mean the degree of the polynomials in the expansion. So here we go to polynomial degree 5. And basically, the black points are degree 4 and 5, and the other colors correspond to different degrees. What we can see is the following. There are many of those coefficients that are, let's say, 10 to the minus 6 or below, or 10 to the minus 5 and below, meaning, well, in practice, 0. But you know just after you have computed them, okay? The problem is that if you said, okay, let's take just the points up to degree 2, polynomials up to degree 2, that is all color points, red, blue, and green, what you see is that you miss a big number of points of terms that are of degree 3 or larger than 3, and in the same time you have a number of coefficients here in your expansion that are like 10 to the minus 8 that are just useless, they are 0. So this kind of truncation is actually not good, not straightforward. So that's why people start especially to solve high-dimensional problems and avoid this big number of terms to go for so-called sparse expansions. And in that case, without entering into details, we can formulate this in terms of solving a least square error that is penalized to sort of regularize the problem and obtain in the end a sparse solution. And then there are many different practical algorithms to do this. We use in most cases a so-called least angle regression, which is something that is very efficient to basically find directly out of a candidate or set of candidate polynomials, instead of computing all terms, or this algorithm determines the non-zero terms directly. And of course, this is much more efficient. Okay, so assume that we have this PC expansion. Now in a minute, I will show you how we can use this for sensitivity analysis. Before this, I would like to introduce another technique called row-rank tensor approximations, which is, well, something more recent, where the idea again is to somehow expand this computational model, but in a different way. Here, we introduce first the so-called rank 1 functions, which look similar to previous equations. It's basically a function of all the input parameters that is a product of univariate functions, okay, exactly as, but not necessarily polynomials here, okay? These are not necessarily polynomials. What we will call a canonical low-rank decomposition of a particular function would be a sum of such functions, possibly with some, let's say, normalizing factor here. So it's a sum of products of univariate functions. And the number of such functions, we call this the rank, R, the number of terms in this sum. So that's the, let's say, format. Of course, we don't know this function now. So if we want to make an approximation, we want to represent this function somehow. So again, we will represent each univariate function here, which is yet unknown, by, let's say, polynomials. It could be something else, but again, orthogonal polynomials are good candidates. So we replace each function by a sum of orthogonal polynomials, but now just in one single variable, okay, each of them with this proper set of orthogonal variables. Polynomials. So in the end, this representation here of the output, it's still polynomial, but it's not the format we have seen before, which is a sum of orthogonal polynomials. Here it's the sum of products of univariate functions itself represented by polynomials. So why do we do this? Because now if we count how many unknowns we have for such a representation, for instance, assuming here that each function is approximated with the same degree, just for estimating a bit of complexity of this approach, you can see that the total number of terms or coefficients are here, the z terms and the b. It's basically increasing linearly with the dimensionality, as opposed to polynomial chaos expansions where it was increasing like exponentially. So this is why people introduced a few years ago this kind of representation, because they have in mind that this way we can handle really high dimensional problems in terms of approximation, maybe hundreds of dimensions, hundreds of input parameters, still at a reasonable cost. This is appealing indeed. In practice, it's not so true, but still, actually, for sure, it's very clear that the number of unknowns is far less. Now, what is the drawback of this representation? As you may see here, the true unknowns of this representation are those coefficients here, where you have products of such coefficients. So it's not anymore a linear expression in terms of the unknown coefficients. So it cannot anymore be solved like a typical regression approach. It's not a linear model anymore. So how do we solve this? We use a greedy construction. So we will add rank 1 functions one by one, starting with a single one. And at each step, what we do is that we have the true model, again, evaluated on a number of points. That's always the same story. We have the current approximation with r minus 1 terms. So we take the current residual. And this residual, now we have to approximate by a function which is this kind of product of univariate functions, which again, we have unknowns that are it's not a problem that is linear in the unknowns. So we use here a technique called alternate least square, in which basically we will, solve sequences of linear problems. So basically we freeze each dimension in a row and freezing all the coefficients for all dimensions but parameter number j here. Everything is known except the coefficient of this function vj. And then we minimize here. This is a very simple least square problem because now we have just a few unknowns, and here p is typically 5, so it's a very small least square problem. And we iterate this. Once we have this, then we fix this and recompute the other ones. And iteratively, it's suboptimal, but usually it converges to some solution. Once we have this new term, that would be the MR term, or not MR, but the correction term for the rth iteration, then we reuse all these terms from 1 to r and sort of recalibrate the coefficient here again to minimize the error. So it's done in 2 steps. And what we get in the end is, let me show it again, this kind of representation. So it's still polynomial, but it's not like the sum of orthogonal polynomials. It's a bit different. What is the point now with all these techniques for sensitivity analysis, which is the topic of the conference? Well, the main point, and you will see now the details, the main point is that once you have one of these representations, the Sobol indices are analytical. You don't need any sampling anymore because of the nice properties of this representation. So they come for free, basically. Why is it so? Well, you all know this so-called Hofding-Sobol decomposition of a model function in terms of constant, univariate function, bivariate, and so on. So it's also what people call HDMR somehow. But here, this is really the exact decomposition in which we can have a constructive expression for all these terms here. You know that these terms in this series expansion are orthogonal with each other, these so-called summands. They are orthogonal to each other. The expected value of any true product is 0. And there is a way to really construct them if we were to do this, although we in practice don't do this or don't need it for the sensitivity indices. But there is a way to do this, which is by introducing this so-called conditional effect. So this is basically expected value condition on fixing a subset of variable to numbers. Okay, so this becomes a function of this subset of variable here, which is any subset of the input variables. And then the terms in the expansion is basically this guy here minus all the combinations for all subsets already taken care of. Okay, so it's a, let's say, iterative telescopic expansion. For instance, the univariate effects, let's say first order, it's basically just this function, the expected value of m given a parameter that is fixed. Okay, so this is a nice construction, and of course, because you have this kind of expression, it's unique. I mean, there is a unique Sobol decomposition of a mean square summable function. Why do we use these properties of orthogonality? Because now if I compute the variance of this big guy here, so mean value would be m0, the variance would be the variance of the sum of this. Due to orthogonality, as you all know, the variance is just the sum of the variance. And this allows to define the Sobol indices as basically the partial variances of each term here normalized by the total variance. So this would be, let's say, the unique effect of a subset of variables. This will be the effect of a group of variables. And there is also what we call the total Sobol indices, which then considers also all interaction of any kind with other, let's say, third-party variables. Okay, so these are the standard definition. Now, come back to polynomial chaos expansion first. The nice thing is that, well, first, just to compute the mean and variance, PC expansions are very nice because based on these formats that I've shown already, now we know everything, we know the basis, and we have computing the coefficients in some sense. Actually, there is also orthogonality properties here. So it's straightforward to show that the mean value of this expansion is actually just the first term of this expansion, psi 0 being here just the constant 1. Okay, so the mean value is just, well, the first coefficient, and the variance is just the sum of the squares of the other coefficients. So this is really interpreting the coefficients of this expansion in terms of, it's a spectral representation somehow. So I don't know, if you're familiar with dynamics, this would be model representation, this will be amplitude of modes, and the sum of squares would be some kind of energy. That's exactly the same here. So we know directly analytically the variance once we have the expansion. Now we can also prove very easily that the summands that we usually never compute because they would be computed with this funny and difficult expansion. Here we have it analytically. It's just a sub-expansion of the polynomial chaos expansion for some alpha here that satisfies some fancy conditions. Okay? That's the same for the conditional effects here. It's just another set of coefficients, but it's basically looking at this polynomial expansion. And for instance, the first order effect of variable x1, you just read in the expansion and take just the polynomials that depend only on variable 1 and nothing else. And obviously, that will be the first order effect of that variable. So this gives us the summand, and then, well, then to compute the Sobol indices, it's straightforward because, again, we need the partial variance. And the partial variance is still a variance of, let's say, a sub-expansion. So again, it will be a sum of squares of coefficients. So in the end, whatever once we have the expansion, whatever the type of indices you want, the first order, higher order, group indices, total Sobol indices, everything is contained in the coefficients. You just have to sum of square certain subgroups of coefficients, and you're done. So that's the reason why there is no sampling anymore, no Monte Carlo scheme. It's exact and analytical. And so that's why, well, it's not very new. That's the old part of my talk. This has been published now for many years, first time about 10 years ago. And it's now very much used in many applications. From the other representation I've shown, this low-rank tensor approximation, I will go fast because they are just, well, funny equations. If you want all the details, this has been published recently. It's well, a bit more technical to get all these conditional means, variance, and everything. So you can see from this format here already the mean value here. If you take the mean value, it's obviously the sum of the mean values. And here, as we have, again, independent variables, this would be the product of the 0 terms of all these expansions. That gives me the mean value. The variance, you, well, just do basic derivations, and you get these terms. Then you need the univariate effects. So for instance, for one component, what it is, it's just fixing one xi and then averaging over the other variables. So this, again, with the property of orthogonal polynomials used in the expansion is quite easy to see. You just get out the function of xi, that polynomial here, and then you average over all the other parameters. You can do this for any subgroup of variable, and then in the end, well, you need to again compute this variance of these different terms here. So what we do here, the direct or the first thing we compute is really computing the variance of these things, so the mean and the square of the mean, which already becomes tricky, and then we recombine them. So in the end, it's just nothing complex, just a bit painful to implement to not make any error, but everything again is contained in the coefficients of the expansion, and you get all indices of any kind at any order. So everything, the complexity of the full analysis is just moved just to get a good surrogate model. Okay, let me show you some results to show that all these things work. This is a typical benchmark function you may have heard already. The Sobol function with here 20 dimensions, where the nice thing is that it's a product of univariate functions, and we have all the indices analytically, so we can benchmark easily. And this here, as you see, is exactly what I call a rank 1 function. It's a product of univariate functions of each parameter. So we expect typically that this low rank representation will work well because it's rank 1, in fact. Here we use typically experimental design of different sizes. You get here estimations of the errors. Just this table shows that indeed for that particular problem where the true model is rank 1, this rank 1 approximation for a given size of an experimental design, it's better. It's typically 1 order of magnitude smaller error. Then you have here a table with the mean and standard deviation obtained from the different points, but you see, for instance, here already with 200 points in dimension 20, you get something where you have, let's say, 1% of error of mean or a few percent on mean and variance. You can then get the Sobol indices. The green will be the analytical values, and blue will be low-rank approximation, and the red will be PC expansion. Already with 200 points in dimension 20, I mean, they are not exact, but they are sufficiently close. Of course, for what we call screening, that is find important parameters versus non-important, you find the first 5 which are important here, and the 15 others, we already screened them out. So here, you can just think it as a screening method in dimension 20 with 200 points. I think it beats even Morris' approach in this case. And then if you want really to get the numbers really like 2 digits Sobol indices here, you may need a few hundred more terms, but then you have, again, all the results. These are total indices. Here it's just a kind of just convergence, or kind of convergence curve, just to show that in that case, LRA converges really to the true value much easier. This would be here the really absolute value of error between the true result and some surrogate-based indices. And here, from basically 500 points in your experimental design, all the Sobol indices obtained from the LRA decomposition are well, just good within 10 to the minus 3, whereas it takes a bit more time if you use PC expansion. Now, another problem in which I would say sensitivity is not necessarily so interesting, but it's just a problem to see how it works in high dimensions. It's a problem in which the physics is the heat conduction over this domain here, where you have basically some conductivity here, some source of heat here, and you want to measure the temperature in another area here. The point here is that the conductivity of the material in that domain is not a constant. It's varying spatially. So it's represented by a random field in 2 dimensions here. It's basically a log normal random field, exponential of some Gaussian random field with some properties here with some autocorrelation functions of that random field. That's really the physics. How do we solve this? Well, this, if we want to go back to the surrogate model approach, where basically you have a number of input parameters that you sample to get an experimental design, blah, 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 we have to cast this problem the same way. So this is obtained by what we call a discretization procedure. So we replace this random field, which is more or less just an infinite set of correlated random variables. We replace this by an expansion that will depend on a finite number of Gaussian variables. So here is the technique which is quite popular in engineering, called the optimal linear estimation. It's more or less, to summarize in 2 sentences, it's more or less a kind of Kriging methods coupled with eigenvalue analysis to just get the most important parameters. So this allows basically, after a kind of pre-processing of the random process here, to get realization of this random process just based on some deterministic spatial function and some realization of Gaussian random variables. The thing here is that if you want sufficient accuracy, you typically need at least 50 or something such random variables. So it's just to show that this would work in high dimension here, 53. These are the modes of this expansion. So these are basically these 2D spatial functions. These are, you can consider as modal fluctuation of the random field. And this is the mesh we use to solve the problem, a particular field. And we are interested in the average temperature in some area. You could think about, let's say, I don't know, a computer chipset in which you want to avoid some overheating somewhere here. And this is what we obtained. So dimension 53 here, we use 2,000 points, which is probably far too much already, but already you can see that out of 53, we get that we have, let's say, 10 important parameters. So important parameters here are the modes in that expansion that are taken into account, and another 40-something parameters where basically we could set them to 0, or to the mean value, but their mean value is 0. Here, of course, we don't have any analytical solution. So how do we make sure that this makes sense? Well, you can come back to really standard simple methods for sensitivity analysis. If you have a sufficiently large number of points in your experimental design, you can just compute, for instance, rank correlation between input and outputs, and at least you should have somehow the same kind of important variable versus unimportant, and that's exactly what we obtain here. meaning that in other words here probably the model is not really nonlinear because we get really very similar results. As I said here, 2,000 points is probably already too much. Probably with 500 points you're happy enough for practical applications, and we are in dimension 50, so which is not bad. We have many other examples, but typically up to typically 100 dimensions or at least 80 dimensions in your problem, because in most problems when you have so many parameters, in fact the problem is sparse. The structure of the model is sparse. That is, if you take on purpose a function for which you have 80 parameters and they are equally important, of course this will not work, or this will work but with a high cost because all parameters are same importance. But most problems, and that's why we do sensitivity analysis, most problems are such that when you have 80 parameters or 100, actually 5 or 10 are important, and all the other ones that you don't know in advance are unimportant in terms of uncertainty. So for those techniques, this sparse expansion, sparse PC expansion, and low rank approximation just work perfectly well. I don't know if I have time to talk about Gaussian processes. 10 minutes, okay, then it's very short. This part is very short because, well, I assume there have been and there will be many other talks on this. The idea of Gaussian process is yet another way to compute surrogate models. So the basic setup is the following. You assume that your model is kind of a realization of a Gaussian process now in the space of parameters indexed by the input parameters of the problem with some, let's say, trend here, which is the mean function of that Gaussian process that we parameterize according to a number of functions. This will be the regression part, for instance, a constant or polynomial trend. These coefficients, of course, will be unknown. And then there is a part related to a stationary zero-mean Gaussian process in which we need to estimate a variance and then a correlation structure. Of course, here this Gaussian measure, again, in the context of uncertainty quantification, has nothing to do with whatever uncertainty is on the parameter x. It's just to represent here the model itself. We have different flavors of kriging, especially if we assume that the trend is constant, it's ordinary kriging. Usually we assume some shape for the trend to better capture let's say, the fluctuations, and so this is called universal kriging. And the other part, the autocorrelation function, we need to define, so we usually select a particular family, and then we try to fit the parameters of this family, so these are typically correlation lengths in this setup. You may know, for instance, Gaussian correlation or general Gaussian or Mattern autocorrelation functions or kernels are the ones that are very often used for this kind of kriging surrogate models. Then how do we fit the model? That is the learning part, the learning part of the study. Again, we need an experimental design. And to get a surrogate model, there are basically two ways to do this, which in the end leads to the same equations. Either you consider that now the prediction of the surrogate model in a new point is basically a linear combination of the observations at the existing point which have been computed through the experimental design, or you can consider or define your prediction in a new point as just the conditional Gaussian process at that point, conditioned on observations, which are in fact computations, at other points in the input space. Okay, so this leads to the same equations. I will not give any details. If you're familiar, you will more or less see the equations. The nice thing here, compared to what I've said before, is that we have what we call a mean predictor. That would be my surrogate models, exactly as I had PCE or low rank approximation, which is a function of the current point. Current point would be x0, and it appears here somewhere in this f0 function and r0 function. And it depends on the other data through this covariance matrix here. So we have this with some nice properties that, for instance, a kriging model is interpolating. If you compute this expression here at a point which is a point of the experimental design, you get exactly the value that you had computed with your original code. So in some sense, it's interpolating. There is no additional error here. So that's nice. But on top of this, you also get the so-called Kriging variance. So that's the variance of the conditional Gaussian process. And this, it has been said yesterday many times, it's somehow a local error measure of how accurate your surrogate model is. And again, we have this nice property that at a point of the experimental design, it's exactly 0, which is, well, expected. You reproduce and interpolate the data. And basically, when you take some new points that is far away from the existing computed data, then this variance is larger. So you have also this nice feature that everything is Gaussian. So on top of having, I mean, you don't get just a predictor or an error estimation. You really get a Gaussian distribution in each point. So you can typically compute and plot so-called confidence intervals. So maybe you have seen similar plots already here. That would be a 1D problem, just one parameter x, where you want to approximate this blue curve. You have just here a set of 5, 6 yellow points. And when you do this, you get this dashed curve, which is, well, not so bad here in the region where we have many points, which is very bad here because we have basically no information. But we also have a confidence intervals which tells us that, well, here it could be very bad and here very bad because we have this huge confidence interval. So this is very nice because we have a built-in error estimation, which is now local, and that's the difference with polynomial chaos expansion or the other techniques, where we had a global L2 error. Here, it's really a local error, and this opens the way to, well, typically what people call adaptive learning or adaptive sampling of experimental designs, because if you know exactly where some error indicators of your surrogate model is large, and now if you want to go into an iterative process, this will give you information where to put new points in your experimental design to get an overall better accuracy. How do we now apply sensitivity analysis with this? Well, then here, unfortunately, we don't have like a nice analytical expressions as we had for PCE. So we have to go back to a simulation-based computation of Sobol indices. One way to reformulate the problem is this reformulation here, in which these conditional variances you can somehow write as the covariance between two vectors, and one vector is basically, well, the output of your model, and the other one is something similar, in which basically you replace part of the input components with an independent copy of those components. So by definition, these two will be dependent or correlated because they share some input components and some of them are independent. And the shared input components are the ones for which you want to compute the index. Okay, so once you have this written as basically a covariance over a variance, then it's very easy to have Monte Carlo estimates of this. So you need two samples of points. You have two copies of vectors here, one first sample and one independent sample, and then we will mix the two. Well, this is really standard notation, and then you have these nice estimators. So there are a number of them that have been provided in the last 15, 20 years, up to one of the recent one obtained and derived by Janon, where basically this one is shown to be optimal and efficient in some sense. So it's probably the one that should be used to get the best accuracy. Okay, so how to use this? Well, you use whatever estimator, this one or another one. In any case here, n can be large, the number of samples can be large because you apply this on the Kriging surrogate. And, well, assuming again that you have a nice Kriging toolbox that allows to do this very, very carefully, you can maybe have millions of points and then have very efficient estimation of the sensitivity indices. Another nice property is that actually, again, you can take advantage of the fact that a Gaussian process is not just a deterministic surrogate model, but it's a Gaussian, conditional Gaussian process. So you can take into account the epistemic uncertainty related to the surrogate modeling into account. And this is carried out by sampling, now not just using the mean value of the Gaussian process, but sampling trajectories of that process. And for a particular trajectory, compute again by Monte Carlo the Sobol indices, and then do this for different trajectories, such as to somehow replicate and then get summary statistics of this. So where is, yeah, this should have been written. Yeah, it's basically these are recent results from Le Gracier, Canamela, Yos, and so on. So these are the way they have developed this. It's of course computationally demanding, because once you have the Kriging model, then you have first to sample various trajectories of that model, and for each trajectory sample all the Sobol indices you need. So it can take a while. Here I just show some results from again this stress structure that we had in a recent publication, where we basically compared all these approaches by Le Gracier, Yos, and so on with our PC expansions. Just to show that, well, in that case in particular, it's quite equivalent in terms of how many runs of the underlying complex model, in that case the finite element models of that structure, you need to get accurate estimation. And here again it's in order of 100 to up to 200, where you get really like 2 to 3 digits accuracy on the results. Okay, yeah. Just a last comment on this. If you are really also interested not in estimating let's say the order of magnitude of the different Sobol indices for Kriging, but really in the value itself and a possible uncertainty in the estimation of this, this approach with Kriging is a built-in approach for epistemic uncertainty. With PC expansion, we can use Bootstrap, in fact, to get kind of same results. Okay, well, now I'm more or less close to the end, not completely yet. Conclusions are, well, the following. If you want to do uncertainty quantification in general and sensitivity analysis in particular with very complex model, there is no real choice but to build a reasonable surrogate model of this first. The nice thing with PC expansion and low-rank tensor approximation is that once you have them, then all the sensitivity indices, especially the variance-based one, well, they come for free. So it's really good to take advantage of this. With these techniques, we are able to really solve, with a few hundred runs at most, few dozens to few hundreds, the problem of computing sensitivity indices for problems with 10 to 50 up to 100 parameters, and this really works. For Kriging, it works as well, except that, of course, Kriging in high dimension then may become an issue, but that does not change the overall philosophy. And then, of course, then, well, to use it, you just need a software to do this. So I have listed here a number of packages. If you are more familiar with R, then there are a number of such packages. If you are more a MATLAB person, then I would like to have 10 seconds of advertisement for our platform called UQLab, which, well, basically contains all these techniques for surrogate modeling, for sensitivity analysis. It's basically a cut and paste of this way of thinking. So this is exactly the scheme you have seen at the beginning of my talk. Once you sort of formalize the problem this way, then the software works exactly like this. Like you define what is your model, your variables just define in a very natural language what it is. You define what kind of analysis you want to do and just run it. As I said, we have all these different modules, PC expansion, Kriging, sensitivity analysis, rare event simulation if you're familiar with this. This is the current online version. In the version that is not yet published, we have now low-rank tensor approximations. We have Bayesian calibration and many other features. Just a few facts. It's something that we started about 3 years, a bit more than 3 years ago. And we released the first version, let's say 18 months ago, and now we have about 600 users of people that have used it all over the world. So it's for us a good sign that this software is useful. And for those of you who really love open source versions of this, right now it's not open source, but the open source version will come very soon. This is a map just to show you that even here, some people use it. So we are here. If you are lost somewhere, this is this blue point here, La Réunion. So maybe at least one, maybe a few licenses here. And finally, this will be my conclusion. My conclusion is that based on this, and also, again, commenting a number of talks yesterday, I think we are now in a stage where there are a number of methods to do sensitivity analysis. But it's quite clear that there are a number of methods that, in most cases, just outperform everything else. So I just quote a recent paper from Thierry. As you are the host of this conference, I think we can be confident in your conclusions. So that's what's written there. That's not me. But I completely agree, of course, with this, that in most cases, this PC-based representation are the most efficient ways to compute Sobol indices. And basically, to sort of prove this, or prove by evidence this, we have opened this online Sobol indices calculator a few days ago, where the idea is that, well, if you are a bit familiar with all this, you could get, with the most limited amount of work, some estimation of Sobol indices. So the idea is that if you have followed all this talk, we need an experimental design to compute a PC expansion, and once we have this, then we have the Sobol indices, okay? So here, this is really a funny, simple web interface for a very simplified case study. Assume that, but this is probably 90% of the problems. You have some model, you have ranges and uniform distribution for all your parameters, and you have computed somewhere a space-filling design, let's say LHS or whatever. So you just get it, open it, or upload it, sorry. Oh, I should have prepared this. I have this somewhere. Somewhere, sorry for this. Yes, here. So here, I took Ishigami function, of course. So that file is basically this, okay? It's an LHS design of 3 variables, uniform, and the corresponding Ishigami function. So I just upload this. Come here. Upload. I hope, yeah. This somehow, well, send a request to our server, and assuming the connection is good enough, in a few seconds, we should get the Sobol indices of that function. So if you're familiar with Ishigami, you will find that these are the right numbers. This tells you that, well, okay, your data is quite good enough in terms of uniformity, so you can be trustful in your design. And if you're familiar with expansion, then a PC expansion, then you have all the results associated to this. So if you want to dig into this here, for instance, is very good because we have an error of 10 to the minus 6, meaning that we have a prediction, the variance of this from the PC expansion is exact up to 10 to the minus 6. So that's why all Sobol indices are correct up to 2 or 3 digits here. And yeah, that's it. So basically, if you are interested in this and you have already applied some techniques, go to this site, upload your data, and then click it, and you will get our sparse PC version of Sobol indices. If you are not in this very simple cases here, for just purpose of demonstration, we limit it to limited number of parameters and not too big samples to get, let's say, automatically results, or very, very directly. If you are outside this, let's say, constraints, just take the full software, UQLab, and then you can do this by yourself. Thank you very much for your attention.
Thank you, Bruno. So if I understand well, people can upload their own data.
Exactly.
On the website.
Just to be convinced that it works.
The calculation, okay.
Yeah.
Very nice. Okay, so we have a few times for questions.
Thank you. Thank you. Very nice talk. You mentioned the use of a Gaussian process model, and I have a question about that. If you take this type of model, and if you compute the Carrion-Love decomposition, you will have an expansion with a basis.
That's the same kind, yeah.
The same kind, but you have something more. You have the eigenvalues that give you some prior on the coefficients.
Yes.
But in your expansions, So where is the prior in your expansion? I mean, which prior can you use on the coefficients of your...
Prior? What
because
prior?
in the Carine-Love expansion, it's a linear...
Yeah.
Yes, okay. So you have the coefficients, and the eigenvalues of the expansion give you the prior on the coefficients.
But these are on the input of my model, not the output. It's an expansion.
It's an expansion. It's a linear expansion of the response, and you have a
No. Of the input parameter. I assume that's why. I mean, I'm sorry, it's maybe confusing with the rest, but it's really a problem in which the input parameter is a random field. Okay. And so
I understand that.
I represent this by a Carine-Love expansion. For instance, it's just an approximate Carine-Love. It's just easier to compute. But
we have two models. You have your polynomial model, which is a linear model with linear parameters.
Yeah.
Yes. And I have another linear model, but instead of having polynomials, I have the eigenvalues of my decomposition. Yes.
Yeah.
Okay. But in my case, I mean, what I mean in my case, in the case of this of a Gaussian process model, there is a prior on the coefficients. So my question is, which prior can you put if you use an orthogonal polynomial chaos expansion? Because from this, you could also consider the construction of a kernel associated with your polynomials. But the problem is that we don't know. I wondered if you had some idea of which prior can you put so that you can really construct a kernel. Which eigenvalues you would put on this. If you take your polynomials as eigenfunctions, you can construct a kernel from that. But you need also the eigenvalues, not only the eigenfunctions. So which
this I mean, this is basically two different problems in this setup. It's really, on the one side, you have a problem in which instead of, let's say, 10 parameters well identified, you have one spatially varying field, and this is infinite dimensional. So to handle this, you need a finite approximate representation of that. The best one is, we know Carine-Love expansion is let's say, the one with the best properties in terms of convergence, decay of eigenvalues and everything. So that's it. You just use it if you have, for instance, that random process. You have an analytical solution of Carine-Love, you just use it. If you don't have, you can have a numerical solution to represent this. This is the Fredholm equation and so on. And my method here is just another way of solving the same problem. But in the end, you get the same kind of equation. And this is independent on the propagation of the uncertainty. It's really on the input itself. We recast the input in terms of something that depends, in that case, on just a set of standard normal random variables, which are the one in the expansion. And then we apply whatever we want, PC, Kriging, or whatever. These are different steps, in fact. I'm not sure I answered the question, but we can discuss, yeah. Okay.
So first, thank you for this complete overview of surrogate models. That was great. Just wanted to ask you, you mentioned Bootstrap. Thanks to Bootstrap, you got confidence intervals. Can you hear me?
I come because I don't hear.
Yeah, the loudspeakers are behind.
It's better here. Yeah.
Or you can come next to me if you want.
Here it's okay.
Yeah, you mentioned that thanks to Bootstrap, you got confidence intervals for your Sobol estimators in the case of
Actually,
PCA.
you can, once you have an experimental design, basically you get a PC, okay? You can bootstrap this experimental design, and then you bootstrap your PC coefficients, and then you recombine them and you bootstrap.
Okay, so the resampling was done over the
experimental design. Yeah.
Okay, and so on each of these new designs you get for Bootstrap, did you have to recompute the whole model, or can you use some techniques to prevent you from? So
if you can do different things. If you say, okay, this is my design, I apply this fancy sparse technique to get, let's say, the best basis and the nominal coefficients. If you have this, and then you said, okay, now I fix this basis, and I just resample the input, this is just a matrix product. So you have the basis, finding the new coefficients, it's matrix product. That's
so it's way faster then?
It's very fast. If you want to also possibly change the sparse expansion to each resampled bootstrap, well, you rerun stuff, but then you can also, I mean, In any case, it's very fast. I mean, here, typical equation run of this, you have an experimental design, let's say a few hundred points as I use all the time. We test polynomials from degree from 1 to 15 with all kinds of sparsity and all kinds of greedy search in this in maybe 1 minute with a laptop. So, I mean, it's extremely fast. And as soon as you have a code that takes more than 1 minute, it's, the main cost is really getting the experimental design. Yeah.
Thank you.
Thank you very much for your presentation. I know I have some friends who are working on meta models, especially on Gaussian process or PC. So recently we have a discussion with them because we are working not on scalar output, but we are generating like 3D models.
Yeah.
A good example is when we calculate heat. So when you calculate your surrogate model, it's for 1 point, average or specific point.
Yeah.
But that question, what we are asking, if there is a process automatic that we can just push buttons for all the map, that means we generate Sobol indices for all points of the grid.
Yeah, so again, I mean, repeating the process for not just a single scalar output, but a vector of outputs, again, can be seen in a brute force way as just repeating the process. So that works. For instance, in the software we have, it's assumed that, I mean, it works even if your output is a map. So it will just repeat for all points of the map and can take a while. Now, if it's, let's say, whatever model that computes 3 different quantities of interest, completely different but of interest, probably you have to do this 3 times independently. If it's a map here, like the thermal problem, well, who cares? All these points, I mean, it's very smooth in space. So knowing the result here is very correlated to next point. So of course you can do brute force and let's say you have 10,000 points and do 10,000 PC expansion, but then it's inefficient. So then we pre-process this output with typically principal component analysis, and then this big vector of output of 10,000 components, we just compress first with principal component analysis. Typically we'll maybe get 5 or 10 components, and then we do PC expansion on those components and we combine. So it gives the same results, but except of repeating 10,000 times the analysis, you maybe need 10 analyses plus somewhere eigenvalue PCA decomposition.
No, yes, exactly. But the question is that we have only for the real simulation, model run that we have done, it's like 500 simulations, because one simulation take maybe more than 1 month, and we have access to supercalculator on 200 of thousands for calculation. So the problem is, are we obliged to make verification at each time, or I can, because when we run automatically the model and generate for all the points, can I get information about the error, about which points is not really computed? I have some errors. Because if I do automatically, sometimes I have to go, maybe I have 500 simulation, it's not sufficient for the PC expansions.
Yeah.
So if I do automatically, I cannot priori know that. So if I do automatically the process, so I just push button, I calculate maybe 100 millions the points, Sobol index. Yeah. Can I get information about where I'm good, where I'm bad?
So with PC expansion, you have an idea of the overall accuracy. And for a variance decomposition, it's enough because you want to be good on the variance and on its decomposition. But it's not local information in which region of the input space you are good or less good. That you don't get directly with, let's say, the pure vanilla PC expansion.
That's why automatic, it's not sufficient. We have obliged.
But that depends. If you want Sobol indices, you don't need this. You need to be good in the variance. And so that's the point. That's the point. Sobol indices is computing the variance and decomposing it. And for this purpose, that's really optimal. Then there are other ways, as we said, using Bootstrap, for instance, you can locally have error estimation. So that's another additional layer. Yeah.
Okay, thank you.